that I have trained with because we're all in the same astronaut class for many years. I consider it a privilege to go out the door and conduct a spacewalk with anyone on board. And so it was absolutely not a disappointment. I think that the correct decision was made to accomplish the mission, to do so as safely and with the most risk mitigation in place as possible. So I think it was a great move. And Ann and I, of course, were up here together, and the decision was made on board. So I would never call the opportunity to contribute to the program by conducting a spacewalk a disappointment in any way at all.
Yeah, can you give me a little more information on the decision-making that was behind the spacewalk and whether or not to cancel it or go forward with one female astronaut and one male?
Interestingly, as Ann and I were able to explain and talk about after the spacewalk, Ann made that decision, and the teams completely supported her in that decision. It was discussed on board, and it was discussed with the teams on the ground, and we're just so glad that we have such a supportive team that all knew that that was the right call to make. And that decision was made, and that call was made after gathering the information on the first spacewalk that was conducted in a series of 3. So it's just wonderful to be working with teams that all see the same priorities and that all know that our main mission here is to do our job safely.
Okay, Christina, you just said you've got 2 medium spacesuits ready to go. Is there a chance that we are going to see Jessica Meyer, Christina Cook, all-woman spacewalk going on?
Yeah, so right now we have 5 EVAs coming up, 5 spacewalks coming up to replace the batteries. So basically to upgrade to the new lithium-ion batteries that will better serve the power supply aboard the space station. Since we have a series of 5 spacewalks coming up, and we're doing that in a short proximity of time, as Christina mentioned, everybody up here is fully qualified to do a spacewalk. So I think that we can see any possible combination of personnel going out the door. We'll all be doing spacewalks, and there'll probably be several different combinations. We still don't know the final assignments for all of those, but yeah, there's a chance that we could be doing it together. Just any of the combinations are a possibility.
Awesome. I am going to take that as a hopefully on my end. Okay, this is a genuinely just curious space question that I couldn't not ask, and it's for both of you. You dream about this and you picture these moments of being in space for years, I imagine. What's the one thing that was the most different from your expectations? The thing that surprised you the most about being in space?
Well, since I just got up here, I think some of the things that have surprised me so far, it's very interesting because, of course, we spend so much time training on the ground, and in Houston, we have a full mock-up, life-size, of all of this. And we also have the Russian segment. We don't have as high fidelity in Houston, but in Star City, we also have a good mock-up of that. So we get there's this level of familiarity when you arrive on board the space station. Okay, I've trained this, but then it feels really, really different. And I think the biggest difference is because we are just using the whole 3-dimensional space in microgravity. When I have been training in Houston in the lab, for example, where we are right now, you're always standing on the deck like we are right now, and you're always working in that orientation. But up here, right now we're on the deck, but then 1 minute I might go over here and be completely in the other orientation like Christina's showing you now. And what I found so far, it's really interesting when you're thinking about the plasticity of the human brain. For me right now, being a newcomer on board, once I know where I'm going and I get into that position, but once I've spent several minutes or a while in that position working, my brain kind of reorients to, okay, feet must be down, I must be on the deck again, but I'm really not. I might be up here. And so after I come out of that position, it takes my brain a minute to figure out my spatial awareness and figure out where I'm going. And from talking to Christina and our other crewmates up here, they've mentioned that, they had the same kind of thing at first, but then at some point your brain sort of shifts And instead of using that map that you've been entrained to in the gravity environment your whole life, instead your brain is kind of picking up on cues using, for example, pieces of equipment, and you know where it is. So even if I'm up there and I come out, I see this piece of equipment, which is the cycle ergometer, so the bicycle that we have to exercise on the space station. And my brain knows where that should be in relation to everyone else, to everything else. And so then I can just continue on and I know where I am. So I'm kind of waiting for that shift, because right now it's really interesting. Every once in a while, the space station kind of flips on me and I don't even notice it. But I think it's going to be really interesting for me as a physiologist to observe that kind of plasticity, how the brain can adapt and change to new environments.
Okay, well, Christina and Jessica, thank you so much for your time. Congratulations up there.
Thank you so much.
Station, this is Houston ACR. That concludes the event. Thank you.
Thank you to all the participants from NASA headquarters and NPR. Station, we are now resuming operational audio communications.
Hi, I'm Lindsay Aitchison. I work on spacesuits. This is Ask NASA, and I'm here to answer your questions. How will NASA get to the moon? Well, we have a brand new SLS, Space Launch System rocket. It's launch day, and all the fire and smoke, all the power. You're up in space, and at that point, you can lose your abort system, so let that go back to Earth. And then one more big push, and now your Orion is taking 3 days to fly all the way over to the gateway where it parks, and now you're ready to start the next phase. This is where you're going to start to unload the science equipment and pull out your spacesuits, and then it's time for the fun stuff. We're going down to the lunar surface. So once you put on your spacesuit, you're going to crawl into the ascent module, and that'll take you all the way down to the lunar surface. Once you're there, go outside and start doing science, geology. You spend a couple of days. Once you're done doing all that, you climb back into your ascent module, take off, and return to the gateway. Once you get back to the gateway, you're going to unpack all of your science and everything you want to take home, put it into the Orion. Everybody truckles back into the Orion, and you start that 3-day journey back home. Why do we need the gateway to get to the moon? We're going to the gateway because it makes a lot of sense for sustainability. That means you can go back multiple times and use it to get anywhere around the moon. You can also use it as a staging point on our way to Mars. How will humans explore Mars? Well, that's actually kind of what we're trying to learn by going back to the moon. In addition to learning so much about how the moon was created, which tells us how Earth was created, we're really practicing all those new technologies and those new ways of living off the Earth before we go to Mars. So once we get there, we'll have practiced everything on the moon, and then we can head out.
So what will the gateway Wi-Fi password be?
Hopefully something easy to remember.
Would you go to the moon?
Absolutely. Do I get to choose who goes with me?
Have you worn an astronaut glove?
Oh, hey. Yes, I have. As part of a spacesuit engineer, we try on all of our own hardware.
How does NASA throw a party?
You plan it.
If you could go anywhere in the solar system, where would you go?
Probably Mars. I mean, it's far enough to be interesting. First one there, but still close enough to home if you have a problem.
What's the coolest thing about a spacesuit?
Coolest thing about a spacesuit is that they're made to fit you exactly so that you can have all the mobility you need to both do your job and stay alive.
Do you have a question for NASA? Send your questions to our experts on Twitter using hashtag AskNASA.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
Leading the way to study where Earth weather and space weather come together. NASA is on a mission that will determine the future of how we communicate every day on Earth.
Broadcasting live from NASA's Kennedy Space Center, you're watching launch coverage of the ICON satellite. Its mission? To study the meteorological frontier where Earth meets space. On your screen is the Pegasus XL rocket, which contains ICON. Approximately 15 minutes from now, this rocket will launch NASA's latest Earth science mission off the eastern coast of Florida into a very unique and unexplored area of space. Hello everyone, I'm Jennifer Wolfinger, and thanks for joining us for this highly anticipated launch. The Ionospheric Connection Explorer, or ICON for short, will help scientists understand the physics of our space environment, as well as protect our communication satellites and astronauts while they're in orbit. The ICON mission is managed by NASA's Launch Services program based here at Kennedy Space Center. What separates ICON from traditional rocket launches is that the Northrop Grumman Pegasus XL rocket will launch from the bottom of a Stargazer L-1011 airplane instead of a stationary launch pad. The Stargazer took off from Cape Canaveral Air Force Station about 45 minutes ago. You can see it there on your screen, with the Pegasus attached to its belly. This aircraft, the world's only operational air launching system, is a mobile launch platform that can be deployed from anywhere in the world. The plane will release the rocket 50 miles off the coast of Florida at approximately 9:30 this evening. This is the first of today's 2 possible drop attempts. What you're seeing now is a bird's eye view of Stargazer's flight path. The path follows a long oval loop, also known as the racetrack. When the plane reaches a certain point on the path, the Stargazer will drop the Pegasus rocket. If the first attempt is a no-go, Stargazer will loop back to the sweet spot and make a second drop attempt by 10:55 p.m., which is when the launch window closes. Now here are a few more quick facts about the mission. Once ICON is launched and reaches 40,000 feet, it will be released in free fall for 5 seconds before its first stage rocket motor ignites. The launch sequence from drop to payload separation will take about 11.5 minutes. The Pegasus XL is over 57 feet long and weighs nearly 53,000 pounds. ICON weighs nearly 650 pounds, about as much as a vending machine. When in orbit, the satellite will travel at more than 4 miles per second. That's almost 30 times faster than a commercial airliner. ICON will study changes in the ionosphere where Earth's weather meets space weather. The satellite solar array is over 8 feet long and 2 feet wide, a little bigger than a common door. ICON will study the ionosphere for 2 years to provide a better understanding of this complex region of space. We are approximately 12 minutes from launch, so let's head over to the Mission Director Center where NASA's Joshua Santora and Malcolm Boston will give us a deeper look at this unique launch. Welcome, guys.
Hey, thanks, Jennifer. Good evening to you and good evening to everyone out there watching us. We're coming live to you from Hangar AE at the Cape Canaveral Air Force Station on the east coast of Florida. And tonight, it's Pegasus Launch Control.
That's right, Josh. Malcolm Boston here with NASA's Launch Services Program, ready to rock.
Can you give us a little update on kind of how the countdown has gone tonight?
Very smoothly. We worked a couple of adjustments, but no real issues, and we're ready to go.
Want to be clear, what you're seeing actually there, that's the nose of the Pegasus. So that's a camera mounted to the bottom of the L-1011. So you're seeing the front edge of that. Obviously, it's nighttime here on the East Coast, so that's what's going on. The big story yesterday was the weather. Today, it is not nearly as big of a story. So we have a few things we're keeping an eye on. Their precipitation has been one of the biggest ones. We can't be flying through rain. We have a 20% chance of violating those constraints. So we're keeping an eye on that, but we'll take a look at the radar. Yesterday, this radar was filled with lots and lots of dark greens and reds and yellows, and there it's very splotchy, which is what we want to see. On the right hand of your screen there in the middle, you can see that red rectangle, or part of that red rectangle. That's the box that we call it. The plane is headed for that box. This is a space out over the Atlantic Ocean, about 40,000 feet in altitude, 10 miles wide and 40 miles long, and the plane has to be inside that box in order to drop the Pegasus. We'll talk more about the process in just a few minutes, but once it's there, it has to be traveling. The plane needs to be traveling at the right direction, speed, and in that space, and then it can launch the Pegasus. Malcolm, can you tell us a little bit about the rocket tonight? Tell us about the Pegasus.
Pegasus is unique, the only operational rocket with that's air-dropped. She's about 57 feet long, a little bit more than that, approximately 52,000 pounds at drop. And this will be the 44th time she's been used to launch something into space for us.
Yeah, we also had up on screen a minute ago, we had an image that had waypoints listed. We call this the racetrack. If you kind of see this, it kind of looks like a racetrack pattern. This is where the plane is actually flying. This is the path that it's flying. You can see there's a circle moving towards the PIP section, and that's the actual, the small one to the left of that is what's moving. That's the airplane. We're actually going to take a look now at a video of this past year. So for the past 11 months, we heard from our pre-launch broadcast a couple days ago that there were some major issues, not major issues, but just issues. We attempted to launch almost 11 months ago. Malcolm, what are we seeing happen here over the course of the past 11 months?
Well, this is footage of Icon being pre-launch checked. At this moment, they're buttoning up to fit inside the payload fairing. But over the past 11 months, we've also had some other activity going on. One is troubleshooting and resolving the issue that scrubbed us out 11 months ago. And the second team has been working on just caretaking of the rocket itself and the spacecraft.
Yeah, we had to fly it out to California. That's the facility where they can actually take the thing apart and really do what needs to be done. So this is them actually repacking the Pegasus on the L-1011 to fly it back out here to the East Coast. It arrived a couple weeks ago, so everybody is so anxious for this launch. Such a high level of confidence of everybody's done their homework, they've done their research, they've worked the challenges, they've all come to this place where they're comfortable and they're confident moving forward. We are actually tuning in. So I want to point out right now that our clock is a little bit off of what was anticipated. And part of that has to do with that we have a mobile launch platform. So we're a few seconds behind where we thought we would be. So currently our clock says we're looking at launch a little bit closer to 9:31. So we're kind of just feeling that out as we go. And that's largely dictated by the pilot's position. So ultimately, the clock is dictated by where he is because he has to be inside that box. So in just a minute, we're going to be listening in. We're going to have a couple polls coming up. But Malcolm, really quickly, can you tell us about the teams that are involved, the 4 teams involved tonight?
Well, yeah, as you said, we have 4 teams. One is the air crew, 2 pilots, a flight engineer, and at least 2 launch panel operators. The second team is the Northrop Grumman engineering team monitoring Pegasus itself. And then we have the combined LSP spacecraft Icon teams that are monitoring the entire launch operation. And our last team is our range safety provided to us by our colleagues at the 45th Wing.
Yeah, the range ultimately responsible for public safety. Correct. So they're looking at things like making sure there aren't boats in the area where our plane is flying. In this case, we don't have as much of a land concern because we're not launching from the land, so it's mostly out over the water and in the air. We are going to go ahead and listen in now. We should have Omar Baez, NASA launch manager, pulling his team.
This is the NLM on the NLMnet for final launch readiness poll. NASA CE.
NASA CE is go.
SMA.
SMA is go.
SMD.
SMD is go.
NASA mission manager.
NASA mission manager is go.
LSP.
LSP is go.
Copy. Teams ready to proceed.
All right, so there you go. You had Omar, again, pulling his team. So all go calls, that's what we want to hear. So he'll be reporting out to the launch conductor in just a minute. We're going to actually jump into a video of the last time we launched a Pegasus rocket. So this is the Cygnus mission. I think you said you actually got to work this mission. Can you tell us what we're seeing here?
So right now we're seeing captive carrier. The pilot's heading for the drop box. Very shortly we'll see the Pegasus release from Stargazer, free fall for approximately 5 seconds, and then ignite the first stage engine. Pegasus is a 3-solid rocket motor, 3-stage vehicle. Each stage will burn for approximately 60 seconds.
So there you go, that drop. Again, tonight we won't get to see this in that way because it's dark outside. So we hope to have something for you to be able to see. But again, it's the nature of launching in the middle of the night. And that's okay. Mm-hmm. Again, we're headed towards that box, and like I mentioned, that clock is jumping around a little bit on us. That's okay. We're just rolling with the punches here. We're just under 6 minutes now, according to the official clock that we're looking at. And so coming up in just a minute, we'll hear Adam Lewis, the launch conductor for Northrop Grumman. He's going to be polling all of the teams to make sure everybody's in a good position. Again, our pilot headed for this box, this fictitious line drawn out over the Atlantic Ocean, 40,000 feet in the air, 10 miles wide, 40 miles long. And so as the pilot approaches there, he will be able to ultimately make that call. And we'll talk about kind of his role. He's got a pretty fun role, and in my opinion, it's a fun role for tonight. But let's go ahead. We're going to actually listen in now. Again, this will be Adam Lewis. You hear on screen. You see the current location, so you can see that red dashed rectangle there to the right. That's where we're traveling towards in PLCH for our launch waypoint. So again, let's listen in to Adam Lewis.
Copy L-5, check 174. At this time, I want to poll for final launch countdown. Rock?
Rock, clear to launch.
Peg?
LC, Peg. The entire Pegasus engineering team and my son Jackson, who turned 10 years old today, are go.
NGLD?
NGLD is go.
NLM?
NLM and NASA are go.
We are go to proceed with final countdown at L-4.
All right, so good to hear that all 4 teams and Jackson are all ready to go. So we're excited for everybody to be on board tonight. We want to take a closer look behind the scenes here at this facility. There you see on your screen, this is Hangar AE. Some call it the telemetry center of the universe. Certainly for rocket launching in America, it is. Take a look at this.
The liftoff is the most exciting part of watching a rocket launch. But what you don't see is the dizzying amount of data sent between the rocket and engineers inside this renovated Air Force Base hangar.
The amount of data that comes through this building is astounding.
Chuck Duvall is Deputy Program Manager of NASA's Launch Services Program, which sends scientific and planetary missions into space. He says here at AE, launch managers can monitor every aspect of the rocket and spacecraft's health, so to speak. Hundreds of thousands of measurements, called telemetry, are displayed on computers in real time. But it hasn't always been so high-tech. 20 years ago, machines scribbled rocket telemetry on paper. Lots of paper.
This record would get to be this thick, and it'd be my job as a co-op student to go upstairs and roll that record out.
Hundreds of feet long.
Yep.
Today, rocket telemetry is far more visual and complex. There are close to 40 voice communication channels connecting launch teams from around the world, and they can view 16 or more high-definition camera views coming from the launch pad, several drones in the air, and even on board the rocket itself. And don't forget about the data. Telemetry is now stored on servers for future reference, and it's so voluminous, playing every launch going back to the early 90s would take close to 32 years. As the chief of telemetry and communications at Hangar AE, Reed DeVerde's group processes and distributes the data to the launch teams. And he says Hangar AE can now handle launching 5 different rockets at the same time, thanks to a multi-million-dollar upgrade.
All right, so a really neat look at the facility that we're being hosted in. I wanted to get back to the pilot tonight. Malcolm, can you talk about his role in this whole thing?
Well, the pilot's busy. He's not only transporting Pegasus and Icon to the drop box, but he's also responsible for Stargazer and his crew on board. And so he's going to be monitoring everything right down to the last second, right down to release, and actually making the final decision on when exactly to drop Pegasus. So he's a very busy man and monitoring a lot of data.
So we mentioned that our clock is moving a little bit based on the position of the plane, but also the pilot, if I understand correctly, he ultimately, like you say, he has to choose the right moment when he knows that things are safe for his crew. So again, even more reality of this clock is almost a suggestion for tonight. There's lots of things that are paced off of this, and we work to this, but lots of important things going on. We're going to keep an eye on this camera you've got on your screen. We should be seeing a fin sweep here any second. Just being able to see a little bit of motion, ensuring that everything's functioning correctly mechanically for this launch. I'm going to let you listen in now and enjoy the last few minutes.
Got negative comm. LPO, LC, voice check on Victor 2. And LPO, LC on 133.8.
So it appears that there's a communication challenge.
PLT, 264.8.
If I understand correctly, Malcolm, it sounds like we're having a challenge communicating with the plane. Is that correct?
That's what it sounds like, but they're working through the checklist, and we'll see a resolution here, hopefully, very shortly.
Count.net, the HIN 11 is in the box.
Copy in the box. PLT, LC for voice check. And launch team, we're going to abort, proceed to the abort checklist.
Okay, so we just heard an abort called, so I'm sure that the teams are going to take a minute and evaluate what's going on here. We're going to just stand by. We're going to try and gather some data really quickly before we speak too soon. I know that there is the potential that we could travel a racetrack pattern to kind of recycle and attempt a second drop tonight. I don't know if that's going to happen or not. We're going to, again, get back to you in just a minute.
Roger that.
Alpha 14 is not required, Elsie.
Coming back to you live from Hangar AE here at the Cape Canaveral Air Force Station. So we just checked in with the assistant launch manager for today, and we're getting word that we are going to racetrack.
Okay.
So they're still working towards confirming a time to launch. So again, there's a lot of things that have to happen in approximately 30 minutes. On a nominal racetrack, that's about how long it takes to get around and make it back to the box. So that's great news. So obviously it's nice to have the capacity to be able to cycle through and do this again. So obviously it sounded like there was a comm issue. They were having issues communicating with the plane. That's critically important. And so I think we're going to go ahead and pass it back over to Jennifer in the studio and get a little bit more information from her about the science of ICON and the instruments on board. Jennifer?
Thanks, Joshua. While we wait for a launch update, let's learn a little bit more about the dynamic zone of our atmosphere that ICON will be studying.
Longing for more space, open skies, and exotic travel? Then look up, about 30 to 600 miles straight up, at the ionosphere, Earth's interface to space. Nestled far above the clouds but below outer space, this little understood destination invites you to explore its many features. Experience both the weather from Earth and the weather from space. Marvel at the ballet of radio waves and navigation signals, like GPS, leaping through this particle paradise. Sit back, relax, and take in the aurora, some satellites, and the International Space Station as they sail by. And you'll want your camera handy for one of the region's signature features, bright and colorful air glow. This daily show is made possible by the ionosphere's own swirling charged particles, because that's what the ionosphere is. It's all charged particles. During the day, enjoy the sea of particles, freshly energized by the sun. As the sun sets, this particle party relaxes and the air glow thins. Our quieter nightlife lets you gaze into clearer skies. The ionosphere is in constant motion, an amazing effect of space weather. Don't miss when solar storms rain down. The storm separates the particles even more, making this colorful region delightfully more dense in some places and stunningly sparse in others. And don't forget about storms from Earth below. Your weather from back home also stirs up this one-of-a-kind destination. Experience the unique beauty of every season as changes in Earth's atmosphere, daily and annually, can create pressure waves, changing the ionosphere's shape and density. Venture to the equator, where our particles are packed in lush and thick. Cruise along a magnetic field line and see how the ionosphere's charged material also interacts with Earth's own magnetic field. Don't miss the superhighway of particles zipping out to space and back down to the planet. This unpredictable parade of charged particles can help you unplug and unwind. This is because the crowd of particles can garble the radio and satellite communications from home. The ionosphere welcomes you to discover more about this little-known region. After all, once you've explored this interface to space, who knows how much farther you'll be able to go.
And launch team, be advised, we have just gotten waypoint P recycle. Again, we lost comm in the last couple of minutes. We've switched our frequency comm to the L1011 to 133.80, and we're going to stick on that for the remainder of the operation. At this time, I would like to poll for concurrence for recommended action, recycle. Rock?
Rock concurs.
NGLD?
NGLD concurs.
And NLM?
NLM concurs.
We'll go for recycle. Check Alpha 25.
Go for a recycle.
And PEG, verify power status.
LC PEG, Pegasus is on external power.
Okay, copy that, PEG. We'll check Romeo 2 complete.
As you heard, we are go for another launch attempt and are waiting for a new T0. We'll provide an update shortly. NASA's Ed Chris Gersh caught up with an ICON principal investigator, Thomas Emmel, to find out why it's important to study the ionosphere.
So, Tom, why do we want to study the ionosphere?
Well, that's a good question. So, the ionosphere is the densest plasma in space between us and the sun. And that plasma has a number of effects on systems that we use every day.
So the coolest part that I like about this particular mission is that you got to have an understanding not only of the Earth's weather, but also space weather, because they're really kind of combining, in between the ionosphere. I mean, that must be really difficult or a challenge for you to kind of understand the ionosphere.
That's right. So space weather is a big topic, and when it stirs up the ionosphere, it's hard to maybe see other sources that are driving these changes in the ionosphere. But 95% of the time, space weather is pretty benign and quiet. We don't have a space hurricane every day. We do find that the conditions in the ionosphere are hard to predict anyway. We think that's probably because there's another mechanism driving the ionosphere, and we think it's the lower atmosphere, actually.
So when you have these storms coming towards the Earth, and you'll be able to make better predictions, let's say for GPS, for communication systems, because sometimes those will kind of get out of whack, or they actually can get damaged during a strong storm.
Well, there's three sort of effects, but some of the major effects are, like you said, are communications. because the ionosphere can get stirred up and become very variable, and then we generally use it to bounce signals off of all the time for long-range communications, and that can be adversely affected. Then there's geopositioning, as you noted, so those users aren't bouncing signals off the ionosphere, they're trying to penetrate the ionosphere from GPS satellites. And those signals can become scrambled as well, and that can affect everyone from people who are trying to drive a combine with a GPS to airlines. And then the third users focused on space weather are power and utilities. So all those currents that the utilities are worried about are currents that are driven because there's current overhead in the ionosphere. So being able to predict that condition in the ionosphere is key for those power operators as well.
Now, when we're talking about the ionosphere, what kind of range are we talking about in the atmosphere?
So that's a good question. So in the daytime, the ionosphere is about 100 kilometers up, or 62 miles. That's where the plasma starts. And it goes all the way up to a big peak about 300 kilometers. The nighttime, the lower ionosphere sort of disappears. It recombines. The sun's not driving anymore. But the upper ionosphere just sits there. And that's what you use to bounce signals off of at nighttime.
And so it's easier to communicate at night than it is during the daytime.
If you've listened to shortwave radio, you can get Radio Moscow or Radio Tehran in the middle of the night. You can't get that in the daytime.
You can't get it in the daytime. Now, Tom, as the principal investigator of this mission, what is your ultimate question that you want to answer?
What I want to understand is why the ionosphere is completely different one day to the next. And we've tried to model it. We don't have the measurements. You'd have to guess. And then maybe you're right or maybe you're wrong. Why is it doing that? So we've never had the data in the daytime and the complement of instruments at the same place at the same time to even approach that question.
Thanks to our NASA Edge friends for joining us. Now we're going to check back in with the Mission Director Center for an update. Joshua, Malcolm?
Sorry, we are recycling through the racetrack, so we're moving towards another launch attempt. We're getting word that should be at approximately 10 p.m. Eastern time. So we're hearing a lot of great chatter among the teams. You mentioned those 4 teams earlier this evening working together really well to be able to get back to the point when we can give this another shot tonight.
That's right, Josh. We've got a large number of checklists we need to work through among all 4 teams, and they're just demonstrating their ability to adapt to a new set of circumstances and work through their checklists and get us back into launch posture.
That's right. We want to give you a chance to see a little bit more about the Pegasus and some of the people involved in that. So our NASA's Daryl Nail caught up with Phil Joyce with Northrop Grumman to talk more about the Pegasus. Take a look.
Thank you, and hi everyone. We're here at the skid strip at the Cape Canaveral Air Force Station in Florida, and I'm joined by Phil Joyce, Vice President of Space Launch with Northrop Grumman. Behind us is the Stargazer and the Icon spacecraft. It's an exciting time to be here. It is launch day, 2 years in the making. How are you feeling personally about that?
Well, there's really no day like launch day. Everybody is just jazzed for this mission. It's been 2 years of hard work. And a lot of trials to get to this point. The team couldn't be more excited and more confident that we're going to have a good mission today.
Let's talk a little bit about the trials. There were some problems that were encountered that you had to overcome during that time. Talk about them and how you fixed it.
Yeah, well, on some previous launch attempts, we observed some anomalous readings in one of our position feedback sensors on the rudder. The rudder is on the top of the vehicle and is what steers the Pegasus during its first stage of flight. They were concerning enough to us and to NASA that we stood down and we did a very long and detailed investigation on the cause of those, determined what that cause was, made corrective actions, implemented those, and that got us to where we are today, ready to launch.
And where we are is standing right in front of the spacecraft and the plane as well. And you can hear our audience, probably the hum of those generators in the background. They're playing a key role ever since it got here and all the way up until launch day. It helps protect the spacecraft. How does it do that?
What you're looking at back there is our launch pad. The L-1011 is a flying launch pad as well as the first stage of our rocket. And those generators are required to operate those L-1011 systems like any normal commercial aircraft, but also to protect the spacecraft environment inside of the Pegasus fairing. This particular spacecraft, the Icon spacecraft, is very sensitive to contamination. And the systems that you hear in the background are providing a clean source of temperature-controlled air to that spacecraft so that we can ensure we have a great mission.
And I hear it's 65 degrees. I'd like some of that controlled air on me right now.
Yeah, it's a little warm out here.
It's a warm October day here in Florida. What are you looking most forward to, and where will you watch the launch?
Well, of course, we're always looking for a successful launch and a happy customer. That's what we're here for. I'll be in mission control with the rest of the Pegasus team, doing the countdown and being part of all of this.
Bill, thanks for joining us. We appreciate
Thank
it. We'll send it back to you in the studio.
All right, so we still are live. You're now looking at the engine end or the motor end of the Pegasus rocket. So this is a camera mounted to the bottom of the L1011. So Malcolm, I wanted to ask you, just thinking about the Pegasus, obviously we're doing a lot of work in the sky right now. What kind of things have to be done in preparation for this launch on the ground or in the sky?
Well, on the ground, starting with on the ground, we need to verify that the components of the system are responding to commands. So for a ground test, we'll move the elevons with external power and communication capability, as well as ECS, verifying we can control the environment around the spacecraft. In the air, we will be verifying the hook release mechanism just to make sure that it's fully charged and ready to release Pegasus on command. Just as an example, and then obviously we are also coordinating comm channels and things of that nature. So all 4 teams are busy right now.
Yeah, it makes a ton of sense. Right now, again, we mentioned that because of just the speed of the plane, whether it be headwinds or tailwinds, we're now trending towards about a 10:01 estimated time to be inside the box. Again, that box being this space over the Atlantic Ocean, 40,000 feet off the ground, 10 miles wide, 40 miles long. So we're moving towards that. We want to actually show you a little bit more about the Pegasus and this launch in particular. So we've done a number of what we call T0 videos. Essentially, this is a series we've done with Launch Services Program missions, where it kind of takes an in-depth look at missions and kind of what all is involved. So take a look at this. This is essentially part 1, because part 2 will be obviously part of the launch.
Where does Earth's atmosphere end and space begin? In a mysterious region of space, scientists call the ionosphere, a volatile place, where terrestrial weather from below meets space weather from above. It's also where our astronauts and critical space assets orbit. Without a proper understanding of this dynamic region in space, the technology and communication we rely so heavily upon could be at risk. That's why NASA is launching the Ionospheric Connection Explorer, or ICON, to give us answers.
The primary goal of the mission is to gain an understanding between the weather here in our atmosphere and in the ionosphere in space. We don't quite have a handle on what's going on up there in the ionosphere, so this will give us an opportunity to understand that.
The ICON spacecraft only weighs 364 pounds, so NASA's Launch Services Program chose Northrop Grumman's air-launched Pegasus rocket to deliver it into a 360-mile-high orbit.
We selected the Pegasus XL launch vehicle. It provided an excellent combination of mission performance and flexibility for the mission design for a spacecraft of the mass of ICON.
What's unique about the Pegasus rocket is that it is an air-launched vehicle, and that allows us to launch from anywhere in the world.
The challenge with processing Pegasus is that it's a flying solid rocket motor. Solid fuel ready to burn as soon as it's ignited.
PLT, LC is go for launch. PLT confirmed.
LC, PLT confirms go for launch.
LC, RTO, countdown net, liftoff, first motion time.
It requires special attention. An explosion-proof processing facility at Vandenberg Air Force Base in California, where the spacecraft must be mated to the rocket and sealed inside its protective fairing. It's one of the few launch systems in the world where the payload is attached to the launch vehicle before it's encapsulated. Once complete, Pegasus is free to launch from anywhere in the world.
Once we've established that we're ready, we then transport our entire launch team and hardware to another part of the world so that we can insert ourselves into the proper trajectory.
But to get there, Pegasus still needs to be strapped to the belly of the L1011 Stargazer. Strapping 55,000 pounds of solid rocket fuel to the bottom of an airplane is tricky, but these rocket scientists and engineers are up to the task. Once Icon and Pegasus are locked and loaded, then it's up to the pilots to fly the Stargazer into its drop zone.
Engine start 2.
So there you go, a little bit of the behind the scenes on this mission in particular with the Pegasus and Icon. Obviously, the next chapter in that story is hopefully going to be written tonight as we're coming around for our next attempt. There on screen, you see the racetrack that we're traveling. So again, we made it inside the box, but had communication issues, and so we called, an abort was called, and so they essentially meant they were going to recycle and run this racetrack. So they've literally just kind of circled around, more of an oval, but definitely circling around there, and headed back towards that box. And I want to kind of recap those the facts we hit earlier. Malcolm, can you tell us a little bit more about the Pegasus rocket itself?
Yeah, Pegasus is a little bit more than 57 feet long from nose to aft nozzle, 52,000 pounds of solid rocket propellant, and this will be our 44th launch. We're excited, ready to rock and roll.
And Malcolm, can you talk a little bit more about your personal experience? You actually have worked on some of the Pegasus missions, correct?
That's correct. Directly on the Cygnus mission and various other Pegasus missions over the years.
Very cool. So we're hearing lots of good chatter. There's essentially after the point when they were able to reset the clock, it looks like we are targeting right around 10 o'clock or so for our expected time to be inside that box to drop. So they're cycling through all of those same processes they did before. Again, it's a choreographed effort. It's something that everybody kind of knows. And literally they called out, turn to this page. So everybody's on literally the same page proceeding through the launch countdown. And so we're going to come back up here in about 30 seconds on Omar Baez's NASA poll. So NASA launch manager Omar Baez, he's going to poll his team. We heard some good chatter from his team talking about making sure that their batteries are in good shape, everything's in good order. So let's listen in just a second, and we'll hear Omar's poll of his team.
And RCO, if we can get a reset of the clock at the L-7 minute call from the PLT.
RCO here, copy.
And this is DNLM with our Delta final launch readiness poll. NASA CE.
NASA CE is go.
SMA.
SMA is go.
SMD.
SMD is go.
NASA Mission Manager.
NASA Mission Manager go.
LSP.
LSP is go.
Copy. NASA team's ready.
All right, there we go. Malcolm, so on your screen you're seeing one of our control rooms here in this building. There are a number of these rooms like this with folks very diligently watching their screens, looking at data. How many people, roughly, Malcolm, do you think are really involved for hands-on tonight?
Hands-on in this building, probably on the order of 60 to 80 people. Everyone watching different systems and different areas of responsibility.
And there you go on your screen now. You see that's the tail end of the Pegasus rocket. This is a camera mounted to the bottom of the L-1011 Stargazer. So we will, once we do drop this rocket, essentially you'll just see that rocket kind of vanish from the view as it's released to fall downward for the ignition. So we are still tracking towards right about 10 p.m. Eastern time for our drop. Continue to hear lots of good chatter, a lot going on. Can you talk about the range a little bit, Malcolm? We talk about the range a lot because it's a big part of making sure we're good for a launch, but what's their role and how are they involved today?
So range safety is primarily responsible for public safety. They're constantly monitoring the position of Stargazer and Pegasus. And after drop, the range will be monitoring Pegasus to make sure it remains in a nominal launch path. And if it deviates, then they're prepared to take action to protect the public.
Yeah, that's so important to remember that they're really focused on public safety. And so obviously, like, we want our spacecraft to be in good shape, we want our rockets to be in good shape, but people are the priority. And we see that top to bottom all day, which is great. As we mentioned, we're working through all those countdown procedures, so we should hear Adam Lewis, launch conductor for Northrop Grumman, chime in here in just a second again to make sure he's polling all of the teams to make sure that we're good to go for a drop attempt number 2 tonight. Let's listen in.
5. Launch team at this time on a poll for final launch countdown. Rock?
This is Rock, clear to launch.
Peg?
Peg is go.
NGLD?
NGLD is go.
NLM.
NLM's go.
Launch team is going to proceed with final countdown at L-4.
All right, so once again there you see on screen our control room. That's actually the folks sitting behind us. Always happy to be hosted here in this space. Malcolm, I wanted to see actually if you could speak to the rocket a little bit. Because it's nighttime, you don't get a great chance to see this rocket and all that's involved there. But we have this expanded view of the Pegasus. We want to show you this on your left-hand side there. Can you tell us about some of the elements of this rocket?
Well, right off the bat, you'll see we have 3 stages, all solid fuel. And the most interesting piece is the first stage with the composite wing and the 3 fins, 2 elevons and 1 rudder. And these are used somewhat uniquely in the industry right now to steer the vehicle during first stage burn. We'll separate at the end of stage 1 burn, ignite second stage, and release the fairing burn for approximately another minute. Separate stage 2 from stage 3 and ignite stage 3.
So again, we're continuing to proceed through the countdown, hearing lots of good chatter, calls for moves to internal power, ensuring all the systems are communicating well. There again on screen, you see the back end of the Pegasus rocket, still targeting right around 10 o'clock for our expected drop time. I want to put up the racetrack again, just to again kind of show you where this plane is, flying very intentionally out there around the Atlantic Ocean. You can see the drop point is roughly 50 miles off the coast here. So there's 2 circles where you see PTRN. The smaller one is moving through the larger one. That smaller one indicates that's the plane's location. So we're getting very close to that drop box. Again, 40,000 feet off the ground, 10 miles wide, 40 miles long. And so proceeding towards that, we're going to be hearing these same calls again and again, which is great. Like these are all really important parts of the equation here. You've gotten to sit on console before, correct, Malcolm?
That's correct.
Can you talk about kind of the experience? Like, what's that like? Especially in a situation like this where you're recycling and there's a lot going on really fast. What's that feel like?
Well, it feels tense. You're watching your data. You're in an off-nominal situation already because you've aborted. But you're watching your system and reporting out. You're listening for the calming voice of the chief engineer or the launch conductor, and making sure that you're prepared to report out your subsystem status. So once you're in that situation, you really focus on all the practice sessions that you've had and making sure that you're ready to rock and roll.
Yeah, obviously. Our job there's definitely pressure here, but certainly it's different when you're back there because you're the ones making sure that this rocket's going to be safe and the spacecraft is going to get where it needs to be.
Absolutely.
There's people that have invested years of their lives, if not entire careers, on these science missions. So we're proud to be a part of this process. As we near our dropping point again, can you recap again for us the role of the pilot tonight?
So the role of the pilot is he's watching and flying his plane first of all, and he's also transporting Pegasus to the drop box, and will be responsible for a final decision to release the vehicle and begin the powered flight for segment of our night tonight.
Sure. Let's see if we can toss up the tail end of that rocket again. I'm hoping that we might be able to catch. They do a fin sweep to make sure that mechanically things are working well. This is about the last time through the track that we lost communication, so definitely very anxious moments here. Again, in this final minute or so, still targeting about at 10 o'clock. I'm going to let you listen in and just kind of enjoy what's happening around us.
LC Peg, go for fin pin retract.
LPO, go for fin pin retract and fin sweep.
LC, Senior MEFCO, countdown L1011 is in the box.
Heading and ground speed are green.
LC Peg, Peg is go for launch.
LC is go for launch, PLT confirm. Stand by. And drop on my mark. 3, 2, 1, drop.
Pegasus away. Vehicle is fully armed. Stage 1 ignition has been confirmed.
Launching ICON to explore and unlock the mysteries of the weather where Earth meets space.
Through transonic, power buses remain strong. Stage 1 fin actuator system is operating nominally and controlling the aerodynamic flight of the vehicle. Coming up on 30 seconds into the ICON mission. Vehicle has passed through max Q. Attitude remains nominal. All power buses nominal. All vehicle subsystems are operating as expected. Stage 1 burnout in approximately 20 seconds. Stage 1 has burned out. Attitude and the flight path are nominal. Approximately 10 seconds until Stage 1 separation. Stage 1 separation confirmed. Stage 2 ignition has been confirmed and attitude is nominal. Stage 2 TVC is operating as expected to control the flight of the vehicle. Approximately 20 seconds until fairing jettison. Fairing deployment has been confirmed. Both halves have been separated. Vehicle attitude remains nominal after fairing separation. Power buses remain strong with excellent margin. Stage 2 motor burnout. Attitude remains nominal. At this point in the mission, the vehicle enters a long ballistic coast phase as it gains altitude, waiting for the proper time to ignite the Stage 3 motor. Good telemetry with S-band on Stage 3. We've got report from GNC that vehicle performance to this point is excellent. The vehicle flight computer is currently recalculating the proper time for Stage 3 ignition.
All right, so there we go. What you're seeing right now is actually an infrared camera that's based here at the Kennedy Space Center, and it's been able to track that. We didn't show you this earlier because there were clouds in the way. So as the rocket flew up above the clouds, we were able to get a picture of it. So we could even see the payload fairing separating come off. So it is a really, really pretty night out. It's nice and beautiful, hearing lots of nominal calls, which is what we want to hear. I want to talk a little bit about ICON now, because as Pegasus will round out its job soon, ICON really does become the star of the show. So a few things. It has about the size and mass of a home refrigerator. It's deployed to about 27-degree inclination at 360 miles in altitude. So that's a little bit higher than the space station as far as its altitude is concerned. And the inclination is especially noteworthy because a lot of these kinds of science missions will have polar orbits, will then move from north to south pole. This one is flying much more equatorially. And it's going to be traveling at over 4 miles a second when it reaches its orbit. That's one orbit every 97 minutes, so roughly 16 orbits every day. That's the same speed just about as flying from Los Angeles to New York in about 12 minutes. So this thing is moving very quickly. I'm very excited for this. Continuing to hear those calls for nominal action, which is what we want to hear. I want to go ahead and actually toss this to a an overview of the ICON mission in general. So go ahead and take a look now about this, some more about the science of ICON.
Up past the clouds, past the stratosphere, and even farther, some 60 to 600 miles above Earth, our atmosphere slowly gives way to space. This region, the ionosphere, is home to the aurora, but is also increasingly a key part of the human domain. It houses not only astronauts, but radio signals used to guide airplanes and ships, and many satellites. And yet, the ionosphere is not well understood. To explore this area of near-Earth space, NASA and UC Berkeley built the Ionospheric Connection Explorer, or ICON. ICON's task is to help us understand just what causes the constant changes we see in the ionosphere. The more we understand, the more we can protect our assets in space. From a position close to Earth, ICON samples variations in the ionosphere over the course of hours, days, and seasons. The mission will investigate how the ionosphere reacts to our planet's weather rising up from below, as well as space weather from above. A key set of the mission's observations focus on the most eye-catching phenomena visible in the ionosphere: air glow, colorful bands of plasma caused by solar radiation. ICON will use specialized technology to track how this plasma is moving through the ionosphere. As ICON learns more about the relationship linking Earth's atmosphere and the space environment, the information will help improve the ability to predict conditions in the ionosphere. One more important step in protecting ourselves as we venture farther and farther from home.
The reorientation maneuver for Stage 3 ignition has been complete, and the attitude of the vehicle is nominal. Stage 3 TVC is online. Stage 2 has been separated.
There you go. Some really great calls there. So we just heard that's the round out of the second stage finishing its job and the third stage beginning its task moving forward. It has a little over a minute to burn as the third stage.
The vehicle.
There again, a great nominal call on that. So everything proceeding well. We continue to hear great reports. The people here, you can feel the energy.
Operating nominally.
Everyone is really excited about this mission and having it on its way to where it needs to be.
Vehicle attitude remains nominal.
What you're seeing on screen is an animation with some data there on the right-hand side, kind of just tracking where this thing is right now on its way to its orbit.
Vehicle is now in orbit.
All right, a phenomenal call there.
Stage 3 burnout confirmation. Attitude remains nominal. Looks to be an on-target orbit for ICON.
Awesome. I'm joined now by Allison Powers, Pegasus business manager for Northrop Grumman. How does that feel to hear that call of we're in orbit?
Wonderful.
We made it. We did
It's a great feeling.
It's been a long time, but it's great. Can you tell us a little bit about your role for Pegasus?
Yeah, I'm the business manager for Pegasus, which includes finance, new business opportunities, and just program control kind of roles.
Sure, that's great. So can you characterize kind of how has today's launch gone so far?
Well, one of our favorite words, as you mentioned, is using, that we use during launch is nominal. It might not sound very exciting, but in our world, it means that everything is looking good and on track. So right now, Pegasus is doing what is expected and doing good.
Perfect. So what's coming up next? What's kind of, because we're not done yet. We have a few more minutes to go here, but so what's coming up?
So what's coming up, we're in a coast phase. It lasts about 4.5 minutes. Stage 3 ignition is being computed real time by the vehicle onboard guidance system based on the flight so far. The Stage 3 burn will last about 70 seconds. At burnout, the Pegasus rocket and Icon spacecraft will be traveling in excess of 17,000 miles per hour and have successfully achieved orbit. About 3 minutes later, payload separation will occur.
Awesome. So when payload separation occurs, that's the victory moment for Northrop Grumman, right?
Not necessarily. This is actually the 9th time that Pegasus has launched a Northrop Grumman-built satellite. So when the Pegasus team's job is done, the Icon spacecraft team will kick in and start its mission.
So hopefully a little bit of a taking a breath to rejoice, but then obviously it's time to get back to work, huh?
Right, yep.
Pretty cool. Again, you're seeing on screen that animation. We said we were in a long coast phase. That's what you're seeing there now. So, Allison, what's next for Northrop Grumman? Obviously, it's been a big year for some other things going on with Northrop Grumman and aerospace. The Pegasus, obviously, this is great. So what's the future look like?
Yeah, so along with Pegasus, Northrop Grumman is actively working ground operations at KSC for our Omega rocket that's under development. We're currently modifying the mobile launch platform, one of them, and the vertical assembly building High Bay 2. Preparing for our launch at LC-39B in 2021. And cool fact, we're actually the first commercial company to utilize the historic vehicle assembly building.
Yeah, we're excited for all of our commercial partners, and Northrop Grumman definitely fits into that constellation for us. We're excited to have them there. Obviously, Northrop Grumman is... Clearly, they know what they're doing. We're here. We're on our way to orbit. We got a great spacecraft to work on. So, Allison, excited for you guys, excited for what's coming with Omega, and excited to see just the future of what you guys are doing. Brand new rockets are always fun.
Thanks. We're always excited to support NASA's critical space missions.
Allison, congratulations to you and the entire team. I'll let you go now and go celebrate a little bit.
Okay.
Once we get that spacecraft deployed successfully, solar arrays are out. So, thanks and congrats again.
Thank you, Josh.
Still no telemetry in the center. Waiting for confirmation of icon separation.
So I'm now joined by Steve Krein, Vice President of Civil and Commercial Satellites for Northrop Grumman. Steve, how you feeling?
Oh, feeling great. So far, so good. Everything, to use Allison's terminology, is nominal. So we're excited about that. And we're getting very close to separation of the what we call the observatory, which is the space vehicle built by Northrop Grumman, and the 4-instrument suite. So it's interesting. At launch, the observatory, there's a lot of inhibits that are actually enabled. We have inhibits on the all the instruments are off. We have the main attitude control system, the reaction wheels, torque bars, all the solar array release mechanisms, solar array drive, and all the transmitters are in inhibit. So we don't have any anomalous deployments or any spurious signals during the launch campaign. But at separation, then an autonomous sequence begins, and the transmitters actually start about 10 seconds after separation. We'll actually communicate with the TDRS network and start giving us telemetry. So we're looking forward to that. It's about to happen, and cross your fingers. All's nominal.
Yeah, it is kind of that. It feels like a cross your fingers moment, but ultimately, you guys are really experienced. You know what you're doing. So,
yeah,
I'm sure again with the last year and kind of the work that's been done, you guys have a high level of confidence that things will turn on like they should.
Yeah, exactly, and that's a very good point. That we had a longer delay than we would have liked before the launch, but we did go through a very I'll say very controlled, very disciplined recertification process. It's called comprehensive performance testing, where we exercise all the elements on the spacecraft and then did a full solar array deployment just to make sure that there'd be no issues when we came to this critical moment, which we're about to come upon. So again, a very high level of confidence, and all is nominal.
Awesome. And so will you play an active role going forward in the science as far as Northrop Grumman's concerned?
Well, certainly we'll be involved. We have a team right now out at the University of California, Berkeley, at the Mission Control Center to help with the initial certification. Following the release, as I mentioned, the transmitter will begin being enabled. The reaction wheels then and the torque bars will be enabled, and the spacecraft will stabilize. And then about a minute after release and separation, the solar array will begin to deploy, and it's a 5-panel array. So it's it takes a little bit of time. We want to make sure it's disciplined and controlled in its deployment.
Sure.
So it's about a 9-minute and 10-second deployment. But once that's out and rigidized and we acquire the sun, really the excitement for the day is over. And then we go into about a week-long process of just going through what I'll call a spacecraft bus certification to make sure everything's nominal, that everything's working as expected. And we fully anticipate that to be the case. And once that's done, then we'll start a 3-week period where the instruments are turned on in a sequential fashion. We verify that everything's nominal. And then finally, at about a month after separation, we start what's called science mode. And really that's, the long-awaited period where we get the really high-value data back from the instrument and begin about a two-year process of really just collecting data and distributing to the science community to get the maximum utility for NASA, the science community, and for the nation.
Yeah. Steve, obviously there's... so appreciative of the technical work that you all do.
Sure.
Again, congratulations on what's happened so far. Again, we have a few minutes left, but I'm going to let you get out of here and go kind of watch this thing kind of unfurl itself and just enjoy it with your team.
Thanks, Josh. It's a great moment, and look forward to mission success. Thank you very much. Yep.
All right, so we are listening closely for updates here as we proceed towards the solar array deployment. We're going to actually let you see a little bit more about the science and air glow.
The night sky is never truly dark. If you removed light pollution, the moon, stars, and galaxies, there would still be a very faint, colourful glow. That's air glow. With cameras, you can photograph it only on the darkest of nights. It's about 1/10 as bright as the combined light of all the stars. From above, it forms a luminous bubble encapsulating Earth. Appearing right at the interface to space, airglow holds clues to how our atmosphere affects weather in space, and how space weather affects humans on Earth. The bands of light span from 50 to 400 miles above Earth's surface. In the uppermost boundary of the atmosphere is the ionosphere. This is where our GPS signals and astronauts travel. What makes this region complicated is that it's constantly changing. It reacts to both energy emanating from the sun and weather near Earth's surface. And as the ionosphere fluctuates, so can conditions in near-Earth space where the space station lies. But spotting changes in the ionosphere is a lot like trying to watch the wind. You need a marker of some kind to see the invisible particles move past. And for that, we have airglow. These colourful lights reflect changes in the ionosphere, and this is due to the way it's formed. Our atmosphere consists mainly of nitrogen and oxygen, and small traces of other molecules. When these molecules reach the upper atmosphere, they're at the mercy of the sun. Ultraviolet radiation from sunlight excites them. They become energized and need to release that extra energy in some way. Atoms that remain energized long enough can emit that extra energy through light. In the lower atmosphere, we don't see as much light. The atmosphere there is dense. So when an atom becomes energized, there's a high chance it will bump into another atom and lose energy in that collision instead of emitting light. But as you travel further up, the atmosphere thins out. And like a game of dodgeball, the longer atoms stay untouched, the more time they have to emit a bright, colourful photon for us to see. That's why airglow is only seen in the upper atmosphere. But it can get even more complicated. Some collisions can produce light too. On the night side of Earth, green light is the brightest and occurs when oxygen atoms become excited through collisions with oxygen molecules. A variety of other complex reactions create red and blue light, as well as UV and infrared light that are invisible to the human eye. Each type of airglow contains information about the composition, temperature, and density of the upper atmosphere, all of which are key factors that can change dramatically and rapidly. So airglow turns out to be a fantastic proxy, illustrating not only how particles move through the ionosphere, but what kinds of particles even exist there, which is key information for helping us tease out how space and Earth's weather interconnect. And that's a great reason for NASA to study this beautiful phenomenon.
All right, I'm now here with NASA Launch Manager Omar Baez. Omar, congrats.
Thank you.
Does this one feel special, or is this just like another great launch for Launch Services Program?
It's another great launch for the Launch Services Program, but an awesome and great one. This one's been a long time in coming. We had some setbacks early on, middle of last year, and I'm glad that we were able to get this payload up in orbit and in a safe condition. We did confirm separation through the spacecraft TDRS link. The orbits look fantastic, and currently they're power positive, so everything looks fantastic for us. And a wonderful Pegasus launch, and like always, when your launch pad is moving at 500-600 miles an hour, things happen, and this time the first attempt got us because we lost positive communication with the aircraft on the ground, and our rule is to abort the flight, go back around and try it again. And we did this once before during the HESI mission back in 2003, and were able to execute it flawlessly today.
Does that cause any additional anxiety among the team when you kind of have to racetrack like that?
I don't know about anxiety. This is a fun launch. It's in my operational function. This is about as good as it gets, and we enjoy it. The anxiety level is higher, the adrenaline's flowing, but what a cool way to fly.
Yeah, absolutely. So thinking about Launch Services Program, obviously this is the name of the game for you guys. What's next?